very excited to be here, to be part of the first ever edition of Voxxed Days in this part of Europe, if you know what I mean. My name is Alex, I'm software engineer at Google, and during my career I've been building distributed systems using different approach to make remote calls. I use REST, I use various RPC tools, and when I joined Google I started to use gRPC, and today I'm going to share with you why using gRPC can be beneficial to you in your project. I'm also a member of the Voxxed Ukraine program committee. As you might have heard already, first ever edition of Voxxed Ukraine is happening this November. If you have something interesting to share, please don't hesitate to talk to us or to submit your talk. If you want to attend it, that can be a great idea as well. We're going to have amazing talks on Java, on build the system, on gRPC and other topics, so save the date. It's happening in 6 months. In the meantime, let's learn what is gRPC. So Google started to use microservices a long time ago, probably even before this term was invented in the industry. And as you know, in microservice universe, every client call results in hundreds of remote calls, and to make all this enterprise communication efficient, Google developed its own framework for remote procedural calls, and it was called Stubby. And Stubby was used inside Google for many, many years. There were several generations of Stubby, and a few years ago, Google released open source version of Stubby, which is called gRPC. So gRPC is a new generation high-performance RPC framework initially developed by Google, and today is part of Cloud Native Computing Foundation. It uses HTTP2 as a transport protocol, and it's built with all the modern requirements to distributed systems in mind. If you're wondering what G stands for, G stands for different things every single release, and at the same time you can be scared of an RPC part. Most of us use some RPC frameworks in the past, and you might remember these times of RMI or AMF, and this experience was usually not very pleasant, was it? So folks, don't worry, gRPC is neither Corba nor RMI. Please remember that and never compare them, because gRPC is built with also lessons learned by years of using Stubby. Lessons in scalability, in performance, in building a tool which is easy to use but easy to maintain for a long time. We can even say that gRPC is not just a tool. First of all, there is a set of principles and best practices how to design a distributed system. And gRPC is built on top of these principles. It gives you out-of-the-box abstractions, implementations for these abstractions, and also it provides you extension points. Using these extension points, you can easily change any aspect of its implementation. You can plug in your customization. You can add new features if you want. And gRPC ecosystem today is not only Google. There are other companies and individual developers who contribute to gRPC. And what makes it even more popular is that not only Java. It supports more than 10 programming languages, including JavaScript, since gRPC web open sourced in beta just a few weeks ago. Let's take a closer look at the benefits it provides. First of all, its performance. Google Cloud Pubs Active used to provide their client libraries built with JSON over HTTP, and when they released gRPC version of their client library, their benchmarks demonstrated up to 11 times throughput improvement per CPU just by switching their protocol to gRPC. So gRPC gives you performance improvement out of the box. And talking about performance, you probably heard that Google is believed to handle billions of remote calls per second, but you know what? Forget about it. Because why do you care? You probably don't, do you? What is important for you is how many requests per second you can handle, not how many Google does. Because when you split this monolith to multiple services, all those calls that used to be in process, they're remote now, and latency and throughput of your RPC solution are kind of important now. So how many QPS you can achieve? gRPC makes this question very easy to answer. gRPC team continuously running performance benchmarks. If you follow a link on the slide, you can find real-time performance dashboards for the latest available release and for the latest development version from master. As you can see in the dashboards, for the scenario under test with gRPC Java and unary calls, you can achieve more than 200,000 QPS on 8 core machines, or even more than 800,000 if you use 32 core VMs. And these benchmarks are run for every single pull request, so gRPC team is able to find any performance regression as soon as possible. And with gRPC users, we always know what throughput and latency we can achieve using gRPC. Actually, it's not the highest QPS you can achieve, but we will talk about it a little bit later. And one of the main sources of gRPC performance is its network protocol. gRPC works over a new generation of HTTP, which is called HTTP2. HTTP2, or we can call it H2, is an evolution of speedy network protocol, originally developed by Google, and inside Google, it was designed to address some of the fundamental issues of HTTP1 or H1. For the sake of time, I will not deep dive into it today, but let me just highlight some of the improvements. First of all, H2 is a binary protocol. It's not text protocol anymore. And H2 can use single TCP connection for multiple HTTP connections that helps to increase parallelism. That's very important, because if you have open HTTP connection between two hosts, with HTTP2 for a new connection, you would need to create new TCP connection. With HTTP2, if you already have open connection, new HTTP connection can just reuse existing TCP connections. It helps to reduce overhead and increase parallelism. HTTP2 also addresses header flag blocking issue, and it has efficient header compression mechanism that helps to reduce protocol overhead. It also has some features like server push and stream prioritization. And to demonstrate the difference between H2 and H1, we can go to sites like http2 demo.io. What you see on the slide is the very same image divided into 180 tiles loaded with H1 and H2. And you can see the difference. The same image, same server. The difference is only network protocol. And HTTP2 is used by gRPC because performance is a first-class citizen in gRPC. So performance is number one reason to use gRPC, but it's not the only reason. And we will talk about other reasons today as well. But let's see how to use gRPC, how to start using gRPC. gRPC is built around the idea of defining a service and its RPC method that can be called remotely. And default out-of-the-box IDL in gRPC is protobuf. It's protobuf 3. Protobuf is an open source binary serialization protocol from Google. By the way, gRPC can be changed to support other IDLs, but let's focus on default implementation now. Let's see how a simple weather service looks like. If you want to write a service that gives us some information about the weather, the very first thing we have to write, we have to create a file called weather.proto, and using protobuf 3 define its RPC method. Let's have getCurrent method, it takes a request, and it returns the response. And protobuf allows us to define some custom options, like what will be a Java package when we generate classes from it. Protobuf available for multiple platforms and programming languages, not only for Java, so you can define a contract of your service in a language-neutral way. Today, there are companies in the industry who use gRPC knowledge protobuf, for example, with 3. And we have to define a request and response message. So protobuf supports many standard data types, and it allows us to define data structures or messages. So our weather request will have a message coordinates with latitude and longitude, and our response will have temperature and humidity, where temperature is a message with degrees and unit. So now we have formal API description of our service. We haven't started to write our Java code yet, but we already have this API. And remember, I brought up a point that gRPC is built on best practices, so having API description before coding is one of them. So all your clients will just use this definition as a source of truth, and they can write their client code, client integration, even before your server implementation is ready. So now we have to use gRPC runtime to generate classes from this definition. With Java, it will be gRPC Java runtime, gRPC Java available for, you can do it from command line, you can do it from a plugin of your build system. There are plugins available from Maven, for Gradle, for Bazel. Let's call our wizard gRPC Java runtime. And we generate abstract service definition. We can generate request, response, and builders for them. We don't need to write them manually anymore. And of course, we can and we will generate client libraries or stubs. And you don't need to write libraries manually because nobody likes to write client libraries. Now we have to implement gRPC service. To implement gRPC service, I have to extend generated abstract class weather input base and write its getCurrent method. It's the same method we already defined in our IDL. So this getCurrent takes a request, but it doesn't return anything. It returns void. Why is that? That's because when we receive a request, oftentimes we don't have a response right away. In real life, we need to call some other services, we need to call database, we need to calculate this response somehow. What we can do until we have response, we can just block the current thread, and when we have all the pieces for the response, we can unblock it and return it to our client, right? So let's see what happens when we block threads. So that's a typical scenario. We have a service. The service has a thread pool of size X, and it blocks thread per request. So first request takes first thread, second takes another, and so on, until request X takes the last thread, and then X plus 1 arrives. If all of these X requests are still in flight, you have no threads left. You just reject this request. So this approach is kind of works, but it doesn't scale, because the number of requests you can handle at any given moment in time is limited by the number of threads you have in your thread pool. That's why we don't return anything to our client, but as a second argument, we take stream observer of the responses. And stream observer is one of the key interfaces in gRPC. It's used by both client and service for sending or receiving messages. It has three methods: on next, on completed, and on error. When we want to send a response to a client, we call method on next, and we can call it from any other thread. When we want to send an error, we call on error, and when we want to complete a stream, we call on completed. So now, when our RPC method, getCurrent in our case, is called, we don't block the thread, we just return the execution right away, and we don't return any response to a client. And when we have a response for a client, we will return it later. And now we can receive more requests than we have threads in our thread pool. This approach is often called the Hollywood principle. Don't call us, we will call you when we have response for you. And when response is ready, we just return it using method on next. We call our client first, third, X, whatever response is ready, and they don't have to be in order. That's why API looks like that. Now we can handle large number of incoming requests. But if we have a response right away, we can immediately return it, of course. We just don't have to block the thread. So the easiest way to do it, we just build a response using generated response builder. We set all the fields, and we send it back to our client using this method on next. And then we call on completed to complete our RPC interaction. So now we have to put the service into our gRPC server. We use native server builder. We set port, we add a service, and we call start. If our server implements multiple APIs, we can call add service multiple times. And that's all we need to run gRPC server. Of course, there are many ways to configure it. There are ways to add interceptors, service discovery, load balancing, configure thread pools. But this is just the simplest possible standard implementation. And now server is ready. Let's create some clients. It's pretty simple. We use native builder again. But in this case, we use native channel builder for others, and port. We created a channel. And channel in gRPC is a logical connection between your client and your service. In real life, you will most likely not create channel for host and port. You will have service discovery, load balancing, and other stuff. And gRPC has abstractions for all that. But let's keep it simple for now. Using channel, we can create client libraries or stubs. And gRPC Java generates statically typed libraries for you. There are three types of client stubs in gRPC. First of all, it's a synchronous client. We can create it using method new stub. Then we have blocking client. We instantiate it using the blocking stub. And future-based stub. It's an asynchronous stub as well, but it has an API based on futures. Don't worry, in real life you will most likely need only one of them, not all three. The simplest client to use is, of course, blocking client. Your weather service has a method getCurrent. We call it, and it blocks the current thread until we have a response. This code is easy to use, but if you don't want to block this thread, we can use asynchronous client. And asynchronous client takes request, and it takes stream observer of the response. And the stream observer has the very same three method, on next, on complete, and on error. And when server sends us a response, we have it in on next method. When request is completed, on completed is called, and if request failed, we get an error in on error method. It's important to understand here that when we call client getCurrent, our current thread will not be blocked. It will continue its execution, and we can send multiple requests from the very same execution thread. And when we have response from our client, on next will be called from another thread, not from the thread we made the request from. This approach, again, allows us to scale number of requests in flight beyond the number of threads we have in our thread pool. And that's actually everything we need. We wrote our server, we wrote client, we see client in the slide. Here is our server. But you will tell me, you know what, that's not very useful because it's not how we write microservices in real life, right? In real life, your microservices have what? Of course, they have downstream dependencies. You call other microservices, you call data storage, you call other endpoints. So your weather service can call temperature service, humidity service, and wind service. And these services can call other services and so forth. So does it look more realistic now? Let's have service definitions for these three services, because the very first thing we have to do when we start writing services, we have to define their APIs, of course. The services will have the same getCurrent method, same of weather service. They take coordinates and return temperature, humidity, and wind. But hold on, our weather service didn't have wind. Did it? We can just add it. We define wind of type wind with index 3, and our existing clients, we can already have existing clients somewhere, right? Deployed in other microservices, or in worse, mobile clients, and we cannot take them out of the market. So will they all break because they don't know anything about this new field? They will not, because in protocol of 3 all the fields are optional. Your old client, if they don't know anything about this new field, they will just ignore it, they will not fail, they will not break. This is how protocol and gRPC give us backward compatibility. Your client will break later and due to your application logic. And let's see now how the services will change. Now we have all these stubs. They use the simplest stubs to use, of course, are blocking stubs. We inject them to constructor, and then in our PC method getCurrent, what we do, we just call them one by one. When we have a response from all three, we create a weather response and send back to our client. There are a few problems in this code. It should work, but there are a few problems. First of all, it's sequential. We have only one outgoing request at a time, temperatures and humidities and wind. And latency of our services is the sum of all three request latencies. Another problem, it blocks the current thread again. So if you want to scale, we can use asynchronous client. This way we will have more requests in client. For this purpose, we can use non-blocking clients or future-based client. Let's do with future stuff, because we haven't seen how to use them yet. We inject them, and then in our getCurrent method, we send three requests in parallel. When we call getCurrent on future stub, it returns as Guava future. This future will be executed when server has a response for us. Then we map this future to another future using method futures transform. And again, it will be executed only when we have a result. And we do it for all three downstream services. We take all these three futures and collect them all into a single future. And this responses future will be completed only when we have responses for all three downstream calls. So we have responses future, and we add a callback to the responses future, and then we have results for all three downstream services. We merge them to one single response and send back to our client. So what we did, we sent three requests in parallel, we collected their results, when they're ready, and we send the response to our client with all these three results combined together. You can ask, how could we send three parallel requests from a single execution thread? What thread will make this response, right? Or what threads will be waiting for an I/O? To answer this question, we have to go back and see how we created these stubs. We used native channel builder. And for the server, we use native server builder. gRPC Java implementation is built on Native. And Native is a network application framework that gives us an asynchronous and unblocking I/O. Native has this abstraction called event loop. There is a thread that handles all I/O events in an endless loop. A number of these loops is usually very small. It's close to the number of CPUs available to your Java process. And when new message arrives from the network, event loop reads the message, and it doesn't process it itself, but it submits the message to the worker executor. And the executor will process the message. And when the executor wants to send some data to the network, it creates a message. It gives this message with a callback to the event loop, and it doesn't wait to the response. Event loop writes the message to the network, and when it receives an asynchronous response, it will return this response to the worker executor using provided callback. That's why it's important not to block the thread, because this way we will block the worker thread. This approach of multiplexing connection in a single I/O thread allows us to decouple I/O from waiting thread, and it scales way much better than thread per I/O. If I go back to the service we wrote, you can ask me, why do we need to call onCompleted after we call onNext? Doesn't onNext mean we send a response already to our client and stream can be closed automatically? Or if it doesn't, can we call onNext multiple times before we call onCompleted? Let's see. So long time ago, even before HTTP1 was invented, Heraclitus claimed that everything flows, and it still does because the world is not static. And weather changes, unfortunately, right? Humidity, temperature, winds, they all change, and they all change independently to some extent. What if we can subscribe to the changes rather than pull them? In gRPC, we can easily add stream modifier to the response, and voila, we've got server streaming services. Now services can send multiple responses to the same request. As soon as value changes on server, you can send a response back even without a new request. But our request is not static as well. We can change our location, and if you want to be notified about the weather new location, we can just add stream modifier to the request. And again, now we can send many requests to our server, or we can send updated requests. We have probably to rename our method, because they're not get current, they're more like observe now. So what we have now? Now we have bidirectional streaming. Client can send multiple requests and server can send multiple responses back. And in general, there are 4 types of APIs in gRPC. First of all, there are unary calls, one request, one response. There is server streaming, one request, multiple responses. Client streaming, multiple requests, single response. And of course, bidirectional streaming. Multiple requests, multiple responses. Now let me show you how to implement and run your bidirectional streaming service. I have some code ready for you. Okay. Just switch to my IDE. Alright. Presentation mode. Okay. So what I have here, I have a streaming service. My weather streaming service extends generated abstract class, and it has observe method. First change you see is that my observe method with streaming doesn't take request as a first argument, but instead it returns stream observer of weather request. And when my client wants to send me a request, it will use the stream observer and call onNext method. This is how I can receive multiple requests from my client. What I do in my observe, this observe method is called when RPC interaction is open between client and service. What I do here, I take all 3 downstream services. For them, I generated bidirectional streaming stubs as well. So, and I observe, I subscribe to them. When I subscribe to them, I provide them stream observer. Everything as stream observer does, it converts received response to a weather response. I can show you. So it just converts using provided converter and send it back to my client of weather service back. So I created the 3 connections to my downstream services, but by this point I haven't sent any requests them yet. How I send them requests? First of all, I return stream observer to my client, and when my client sends me a request, I receive this request in onNext method. What I do in onNext method, I just fan out this request, I just let all my downstream services know that I received the coordinates. I just call onNext and their stubs. Now let's go ahead and try to launch it. Not server, just streaming server, right? Streaming. So my downstream services, temperature, humidity, and wind, they will send me an updated values for temperature, humidity, and wind with some delay. So, but to see what's happening, I have to launch my client. So here's, I have my client. So I created a stream. I called observe. So when I call observe on my client stub, I give it stream observer of the response, and when I receive a response, on next method will be called, and what I do on next, I just print it to standard output with async client on next prefix. Now let's go ahead and launch. Streaming client is called client. And if there is an existing connection between my streaming client and streaming server, again, my new connection, my new HTTP2 connection will not create new TCP connection. It will be able to reuse the very same TCP connection that is already opened for another call. So that's another way to scale HTTP2 and gRPC calls. Now you see it's happening. We receive some temperature, humidity, and wind values with bidirectional streaming. So this is how simple bidirectional streaming implementation in client look like in gRPC. Let me go back to my slides. You can ask me, do you even need streaming? Most likely you do, because the world is not static. Use cases can include messaging applications, real-time lead reports, sport results, market quotes, data from your smartphone devices, many more. Think about your project. You probably have some use cases for streaming your projects, and you're probably already solving them somehow. And what is also good about streaming is its performance. Performance for streaming calls is even better than for Unary because it's much less overhead. As of yesterday, for streaming RPC for the scenario under test, you could achieve more than 600,000 QPS on 8 core machines, or even more than 2 million QPS if you use 32 core VMs. And what else you see on the screen? This is not only for Java, you see Go, you see C#, and yes, gRPC supports more than 10 programming languages. And gRPC will generate service definitions and client stubs that can be used in all these languages. And it allows you to write services in different languages. It gives your teams more freedom and flexibility. You can write prototype of your service in Python and then rewrite it for production in Java. And your clients will not even know. They will just use the same client libraries as long as you use the same IDL. Or some of your services can be written in Python and some other in C++, for example, and will be transparent for your client. So now you can have your gRPC calls all the way through your backend, microservices to your clients, including mobile clients and web clients. So you can think that with throughput of million QPS, we can handle we can write as many microservices as we want, right? Every single call now can be remote. But now we have to think about fault tolerance, because network issues are not limited to latency and bandwidth. When we split our monolith, we significantly increase number of remote calls. Every network call is an integration point, even if it's blazingly fast. Integration points are considered to be #1 killer of your software system. When we design a service that interacts with other services, it's not our job to eliminate every possible source of failure simply because it's impossible. Our job is to be able to protect our service from other service failures. Because in distributed system world, it's not if a failure happens, it's when a failure happens. And to be able to protect our service from other service failures, we have to follow some simple rules and techniques, and today we will cover some of them. First of all, it's very obvious rule. Use timeouts. Use timeouts for every integration point of your application. Integration points include I/O, disk I/O, RPC interaction, database call, everything. So timeouts isolate failures and help to protect our service from other service failures. This advice is very obvious, but using timeouts in microservice universe is not as easy as it sounds. Let's say our client has a gateway service, which is blue on the slide. Client calls it with a timeout of 200 milliseconds. And blue service makes 3 network calls. And every service down the stack calls another and third service. What timeouts should we use for this remote calls? The simplest way is just to apply this default timeout of 200 milliseconds to all those calls, right? Because if you know that our client is willing to wait only like 200 milliseconds, there is no reason to wait for more than 200 milliseconds. Will it work? If all our downstream services are fast and latency is low, it will. Like on the screen, total latency is 130, but we need timeouts not when everything is great, when not everything is fast. We need timeouts when something is wrong. Let's see what can happen if not all of our services are fast. We have a client call with 200 millisecond timeout, and it takes 30 milliseconds to call the first service, 80 milliseconds to call the second, and 100 more milliseconds to call the third one. What happens? It's 210 now. Timeout on client exceeds. And our services have not even started to reply yet, but client is not waiting for the response anymore. And at this point, it doesn't listen to my service. But services are still working because we have this default timeout of 200 milliseconds between our services. And what happens when client receives a timeout? Most likely, it will retry. But remember, our services are still doing this processing of all requests, and now they have even less resources to process my new request. And if retry fails, client can retry again and again, and all those retries can overload the system and can lead to cascading failures. And they can cause a major outage of the entire system, even when we use timeouts. So default timeouts are probably not the best strategies. What we can do instead? We can try to tune timeouts for every service in our call chain. But what should be these values? We can just try to decrease timeouts down the stack, right? Because if you know clients waits for 200 milliseconds, we can give first call in this chain 190, then 110, then 50 milliseconds. Sounds reasonable? Let's see. We have this predefined custom timeouts, and client still calls us with 200 millisecond timeout. Let's assume the first request takes 30 milliseconds, the second takes 80, and the third one takes only 25 milliseconds, and the last service replies in 30 milliseconds. So for the last service, request plus reply took 55 milliseconds, and we already reached our custom timeout of 50 milliseconds. RPC failed, despite the fact that our client can wait for the response. It's still waiting for the response. It's 200 millisecond timeout is not reached yet, but now we have to return some response to our client, some error to our client, and most likely it will be something like timeout error. Going back to the original question, how should we distribute timeout? And what makes it even worse is that in real life, the topology is not that simple. We assume that our call flow is that simple, but in real world, our call hierarchy is something like that. And oftentimes we don't know in advance how many of our calls every request will make. It depends on multiple conditions and your business logic. We made another assumption. We assume that we know what our client timeout will be. But oftentimes we don't know. Different clients can call our service with different timeouts. Some clients are latency sensitive, some others are latency tolerant. How should we distribute this timeout? As we saw, none of these strategies were good. So now let's see how gRPC helps us to approach this problem. How timeouts are implemented in gRPC? They're not. gRPC Java doesn't support timeout. But it does support deadlines instead. If you want to specify a deadline for your RPC, you call your client with deadline after 200 milliseconds, get current, and if you do it, we make a call with 200 millisecond deadline or timeout. What is a deadline? Deadline is a fixed point in time by which our client is interested in the response. It's like a timeout, but unlike timeouts, they're not relative, they're absolute. And when this deadline is reached, RPC will be closed with deadline exceeded status code. But what is interesting here, that this deadline is automatically propagated to all the services down the stack. Let's see how it works. If our client makes a request with deadline after 200 milliseconds and current time is 0, deadline is 200, so this remaining time is 200 milliseconds, it's actually our timeout. It will be sent with a request in request metadata. And if our gateway spends 60 milliseconds to process the request, when it makes an outgoing call to the red service, current time will be all 60, deadline 200, and remaining time is 140. And this 140 millisecond will be sent again in the request metadata, in headers, together with the request. And if next call took 90 milliseconds, when red service makes an outgoing request, the current time is 150 now, and deadline is still 200. This remaining value of 50 milliseconds is sent again. And the yellow service processes the call in 60 milliseconds, and now yellow service is ready to call the green one. But current time is 210 already, and deadline is still 200. Our client told us it would wait until 200 only. At this point, gRPC will automatically cancel all network calls with deadline exceeding status code. And it will not even try to call the last service because it knows that nobody is waiting for the response anymore. And this green service is happy, the system is healthy and idle, and it's ready to process new requests. This is exactly what we wanted. And in gRPC, we get it absolutely for free. So gRPC deadlines are automatically propagated. gRPC will automatically change timeouts for the next call depending on the time already spent. And even more, on our server side or receiver side, we can check how much time we have until our deadline. If we have database call or REST call, what timeouts should we use for these calls? We can simply check how much time we have until our deadline and apply this value as a timeout for our database call. We can even subscribe to deadline, and if we provide a lambda to run an expiration message, that lambda will be executed when deadline is exceeded, and we can clean up some resources, cancel some calculations, and so forth. And if deadline is something that we expect, more or less, what should we do if our calls are cancelled? User pressed cancel button, or client application can crash, or internet connection can be lost. There are plenty of reasons for the request to be cancelled. And request to our servers oftentimes results in multiple RPCs to other services. And if our client cancels the request, we don't want to keep all these downstream RPCs active, right? We want our client call cancellation to be resulted in outgoing call cancellation for the same request. This is called cancellation propagation. And again, gRPC gives it to you out of the box. And you don't have to specify anything. When your incoming RPC request is cancelled, outgoing RPC request made from the context of this call will be cancelled automatically. They will all fail this cancel status code. And server always knows if request is valid. You can even access this cancellation status. In fact, our stream observer has more methods than on next and completed on our error. If you want to get an additional API, you can cast it to server call stream observer, and we have additional methods like it's cancelled that will give you true when client cancelled the request. And using this API, you can even subscribe to client cancellation and clean up some resources, cancel non-gRPC calls, stop some calculations, and something else when the request is cancelled. And cancellations and deadlines, they help us to prevent some catastrophic failures after something bad happened. But what if we want to have more control, even before something bad happens? Let's see what can happen when we have bidirectional streaming and server produces more data than clients can consume. So client sends a request and server has lots of responses. It sends all of them back, but if client is not able to process them all, it can fail. So stream will be closed and with some status code. On the other hand, client can send more data than server is able to process. If server is slower than the client sends a request, then server replies, and then client has multiple requests, and it sends them all. And if server is not able to process them, it fails, and now client receives cancelled, unavailable, or another error. To avoid this kind of issues, we want both client and server to be able to negotiate how many requests each side can process. It's called flow control, back pressure. If client knows how many responses it can receive, it can ask server to send up to this number of responses and not more. When client has a request, it can send this request together with the number of responses it's able to process. And when server has them, it sends all these responses back, and then client can request more responses. It can ask, give me 2 more responses, even without sending new requests. And And then server can send these two responses back. And both sides are happy and alive. Same thing can be done in the other direction, of course. Server can tell a client how many requests it can process, and client can send up to this number of requests, and everything is good and everyone is happy again. And of course, with bidirectional streaming, we have both client and server-side flow control. And gRPC supports both client-side and server-side flow control. In this example, you see client-side flow control. Let me explain it. First of all, we need flow control. We call observe method not with simple stream observer, but with its sub-interface, client response observer. And client response observer extends stream observer to add one additional method before start. This method will be called before RPC interaction starts. And inside this method, we can call disable auto-inbound flow control on the outbound stream. If you do it, we enable manual flow control. Now we have to tell our server when we are ready to receive responses and how many messages we can process. We can do it using the request method of call stream observer. You can see it on the bottom of the slide. When we call request stream, we ask our server to send us up to 3 messages back. And when we receive the 3 messages, we will process them with the same method on next as before. It's pretty simple. That was the client side. On server side, we also need more than 3 methods on next and completed on error. That's why you cast your stream observer to server call stream observer. And server call stream observer gives us some additional methods, including method for flow control. We can call set and ready handler, give it a lambda expression, and this expression will be called every time client is ready to receive a request. And we send the response from this method. We just don't send the response immediately to our client, we just send it when the client is ready to process our response. That was client-side flow control. And for the sake of time, I will demonstrate server-side flow control. It's pretty similar to client-side. So flow control helps us to balance producer and consumer, client and server, and gRPC supports both client and server-side flow control. And manual flow control is disabled by default. You can enable it when you need it and when you know what you're doing. And what else should we remember when we decided to split our monolith? With microservices, we solved one issue and acquired new ones. It's not only performance and fault tolerance. Some of the things were much easier to do before we switched to microservices, so let's see how gRPC helps us to approach some of these new challenges. With microservices, we need a way to discover our services, of course. And even more, we usually have multiple instances of the same service, and we have to choose what instance to call depending on load or something else. So we have to solve service discovery load balancing. And gRPC allows you to plug strategies for both service discovery and load balancing into your channel. On a high level, you still work with a single client stub. And your stubs, they don't know anything about service discovery, load balancing. Channel does it. Remember, I told you the channel is a logical connection between your client and your service. So on service side, there can be multiple servers. But you still work with one single channel and one single client stub. If you want to customize your service discovery and load balancing and you don't want to depend on DNS-based solution, you can drop host and port when you create a channel and you implement 2 interfaces. Name resolver is your load balancing strategy and load balancer is your load balancing tool pretty much. And gRPC will do the rest. gRPC has some default implementations out of the box, but if you need to customize the way you discover your service or balance your load, or you have client-side load balancing, for example, you can implement these interfaces and plug them when you create a channel. And again, it's not limited to DNS-based solution. One more challenge we will face in microservice universe is testing. Because we need a way to exercise all these downstream dependencies without relying on network communication. Network adds latency and unpredictability to our test. And even more, what used to be synchronous is asynchronous now, and we need tooling to simplify testing. And gRPC provides you testing tooling out of the box. It gives you some classes for testing your streams, your metadata, utility functions for unit testing, for integration testing. And one of the most interesting and useful tools for testing is in process transport. It's fully functional transport. with all the features, but it doesn't create real network connection. And in our test, you create just like in-process server using in-process server builder instead of native server builder, and in-process channel, and you use it as a real channel. And now your test can make RPC calls without real network communication. And test now can check client logic, server logic, interceptor logic, but they will be fast and reliable at the same time. They will not use network at all. If you use JUnit, there is even a rule that helps you to start in-process server. It makes it even simpler. And there are much more features that we didn't have time to cover today. For example, integration with monitoring system or with distributed tracing solutions like Zipkin, Open Tracing. There are interceptors for adding some cross-cutting functionality, authentication, and many more. And today there are many companies in the industry that use gRPC, it's not only Google. And your company logo can be here as well if it's not here yet. So please try it out. Check out gRPC website, check out demo repository. It contains examples that I showed you today and even more, including examples for flow control. gRPC.io Google group is one of the best ways to reach gRPC developers and users and ask you questions. If you ask a question in this group, you will most likely receive response the same day, or worst case next day. And don't hesitate to contribute. If you find it useful, you can check out gRPC ecosystem GitHub repository and start making gRPC work even better. To summarize what has been said, I will not read this slide, you will do it yourself, but as a summary I want to say that microservices are not free. They brought us a lot of new challenges, and gRPC helps us to simplify these challenges. After all, the tool makes the man, and choosing the right tool is important. I hope gRPC will come in handy when you build your microservices. Thank you again for being here today. I hope it was helpful. I'll probably have a few minutes to answer your questions. The difference? Our runtime is different. As a question, the question was, what is the difference between Java implementation and C++ implementation? Oh, performance difference. That I don't know. That's probably gRPC team did their best to optimize for Java. I remember, like when I started to use gRPC, C++ implementation was better in terms of performance. Now you see Java is better than C++.
When you've demonstrated gRPC deadlines, you've shown that timestamp is passed with each request. How is time synchronized between different servers and clients?
Sure. The question is how time is synchronized when gRPC propagates deadlines, right? So the solution is simple. gRPC team didn't try to reinvent the wheel and to implement some time synchronization. Instead, network latency is pretty much ignored. What is sent as a response in metadata in the header, in HTTP to header, is the remaining time, is timeout, right? And then on server side, it applies to current time. So even if you have like different time on different servers, it will still have this timeout propagated. But as a downside,
so
yes.
the timestamps are not passed actually.
Sorry?
So the timestamps are not actually passed. Only the remaining time in the seconds or something.
Yeah, which is a timeout effectively, right? For you as a gRPC user, you don't see this timeout. You specify deadline, and deadline is absolute value. You can check what is an absolute value, right? But this relative time, this timeout is sent in the response, is what is sent. As a downside, of course, you lose network latency, right? You don't count this network latency.
Okay, thank you.
But that's a solution to make it simple.